This topic will look at different conic sections, including a circle, an ellipse, a parabola, and a hyperbola. We will look at how these can be obtained by taking slices through a cone, and also look at how to find any intercepts or asymptotes of these curves. For each of these curves, try to match them to their equation. You might like to consider things such as where they cross the x or the y-axis, or whether there are any values of x and y where the curve cannot exist. The first three set of curves represent different circles. You may be able to see how the centre and the radius relate to the equation of the circles. We will look more into these in this lesson. The next three represent ellipses. Again, you may be able to see a connection between some of the values in the equation and the curves. The next three represent parabolas. You will see that these are different from parabolas we are used to, as these are parabolas in terms of y squared rather than x squared. The next three represent hyperbolas. These are known as rectangular hyperbolas and have vertical and horizontal asymptotes. The final set also represent hyperbolas, but these have diagonal asymptotes. We will look more into the equations of all of these in this session. We're going to start with a cone shape and cut slices through at different angles to see if we can form different shapes. These shapes will be known as conic sections. First, you will see, if you cut horizontally across, you form a circle. So a circle is the first type of conic section we will look at. Cutting through at a slight angle gives us a slightly stretched circle known as an ellipse. If you cut at a deeper angle still, we arrive at a parabola shape. Cutting down vertically gives us part of a hyperbola. The second part would come from an inverted cone above this cone. The first conic section we're going to look at is the ellipse. Each of these equations represent ellipses. A circle is just a special kind of ellipse. The general equation for an ellipse is x over a all squared plus y over b all squared equals 1. These can be rearranged in a variety of different ways. And also, if a and b are equal, this would give us the situation where we have a circle. By calculating where the ellipse crosses the x and the y-axis, by letting y or x equal 0, we can find the places where it intercepts with the axes. So the ellipse crosses the coordinate axis at a0, minus a0, 0b, and 0, negative b. And as previously stated, if a and b are equal, the ellipse will be a circle. Another way to find the intercepts with the coordinate axes is to first of all rearrange the equation of the ellipse so that it is in the form x over a all squared plus y over b all squared equals 1. You may need to use surds in order for this to happen. So in the case of the first one, we're going to start by dividing by 7. This is so that we have a 1 on the right hand side, which is essential to write it in this form. We're then going to factorise so that we have x over root 7 squared plus y over root 7 squared equals 1. We can then compare to the original form of the ellipse, and we can see that a and b would both be root 7. We can then conclude that the ellipse crosses the coordinate axes at root 7, 0, negative root 7, 0, 0 root 7, and 0 negative root 7. We can also rearrange the equation of an ellipse in the same way. For example here, again we need to make sure we have a 1 on the right hand side, so we're going to start by dividing by 15. We're then going to rearrange this so that we have the form required. So we could write this as x squared over 15 over 2 plus y squared over 15 over 3 equals 1. This has come from the fact that dividing by 15 over 2, for example, is the same thing as multiplying by 2 over 15. And dividing by 15 over 3 is the same thing as multiplying by 3 over 15. Again, we need to use square roots in order to write this in the form required. So these are the coordinate axis crossing points. Clearly these can be simplified. For example, 15 over 3 can be written as 5 in these situations here. Now pause the slide and calculate the intercept with the coordinate axes for each of these, either by rearranging into the required form or by substituting x equals 0 and y equals 0. So the first one has the intercepts shown here, second one here, the third one, and the fourth. Next, we're going to look at the equation of a parabola. Now we are used to seeing parabolas in the form y equals ax squared, but these parabolas are in the form y squared equals 4ax. We're going to look now at exactly why it's 4ax and not just ax. This isn't technically needed, it's not on the specification for further maths, but it is interesting. It does give an insight into how the equation works. So a parabola is defined as the locus of all points that are an equal distance perpendicularly from a straight line and a point. We're going to look graphically at what that means. So here are some coordinate axes. We're going to choose a point on the x-axis and a line parallel to the y-axis. That point and the line are an equal distance away from y-axis. So the origin is the same distance away from both the line and the point. We're going to look at other points that are the same distance between the line and the point if we go horizontally across from the line. So for example, this point here satisfies that, as does this point here, as does this point here. So we can see as we keep drawing horizontal lines across from the vertical line we've chosen, we can also continue this in the negative y direction. And we can see the shape that's formed is a parabola. This is a reflection in the line y equals x of the kind of parabola that we are used to working with. Y squared equals a multiple, y equals a multiple of x squared. So the point here is called the focus. Its coordinates are a0. The line is called the directrix. its equation is x equals negative a. So this part is not technically on the specification, but it does help to understand how these parabolas work. If the distance between the focus and the curve had not been an equal distance between the directrix and the curve, we would have ended up with either an ellipse or a hyperbola instead. You may like to investigate this. So we're now going to derive that equation for the parabola from this diagram here. So first we can find the length of the line to the directrix. So if xy is a point on the curve, we can say that this distance is a plus x, because this distance here is a, and then this distance here is x. Now, because we know that this is equidistant, it's the same distance to the point, the focus here, we can say that this is also that same distance. However, we can also calculate that distance using Pythagoras' theorem. The difference in x is x minus a, the difference in y is y, so we end up with x minus a squared plus y squared square rooted. These two things are equal, so we can put them equal here. We can then square both sides and expand out the expressions. We can then simplify, and this leads us to y squared equals 4ax. We're now going to look at the equation of a hyperbola. As we previously mentioned, there are two types of hyperbola to look at. The first one is the one that has a vertical and a horizontal asymptote. This is a rectangular hyperbola, so generally speaking, a rectangular hyperbola has the equation xy equals c squared. The reason we would say c squared rather than just c is because then we know that c squared is definitely a positive number. We could always put negative c squared, which would definitely be a negative number, and this would just give us a reflection in the x or y axis. This hyperbola has two asymptotes, x equals 0 and y equals 0. It also has vertices. These are the closest points to the origin. They are at CC and negative C, negative C. For example, this hyperbola here has vertices root 2, and negative root 2, negative root 2. The other type of hyperbola here has this equation. You'll notice it's almost the same as the ellipse equation, except there is a minus in between the two terms instead of a plus. This hyperbola has diagonal asymptotes. The equations of these asymptotes can be found using the values of a and b from the equation. The asymptotes are y equals b over ax and y equals negative b over ax. So we can see that the asymptotes always go through the origin, and they are also reflections of each other in the y-axis. This is a symmetrical curve. This hyperbola has vertices at a0 and a minus a0. These are also the places where the hyperbola crosses the x-axis. Notice that it doesn't cross the y-axis because when x equals 0, there are no real values for y. We're now going to derive the equations for the asymptotes of a hyperbola. This is not something that you will be required to do, but it does help to give a good understanding of where the equations come from. So we know that the equation of an asymptote will be of the form y equals mx. That's because it's a straight line passing through the origin. We know that we've got a symmetrical graph, so we will have y equals mx and y equals the negative of mx. We're going to consider what would happen if we took a line with a slightly smaller value of m. So if it was a slightly shallower gradient, then we can see that that line would intersect the hyperbola. Whereas if we took a slightly steeper value for m, there will be no intersection. Similarly with the other asymptotes, if we took a slightly shallower gradient, there would be an intersection, or there'd be two intersections with the hyperbola. But if we took a steeper graph, steeper line, there'll be no intersection. So m represents the limits at which there would be an intersection of the straight line with the hyperbola. If we can find those limits, that will give us the value for m. So we know the equation of the hyperbola, x over a squared minus y over b squared equals 1. Because we are looking for an intersection, we're going to substitute mx in for y. So we end up with this equation here. We can pull out a factor of x squared to give us this. We can then get this over a common denominator. So we end up with b squared minus a squared m squared all over a squared b squared inside this bracket. We can then multiply across by a squared b squared to give us this. Now, because a square number will always be positive, we know that x squared and a squared b squared will always be positive. So therefore, if we have a positive number multiplied by something equals another positive number, we can conclude that this thing must also be positive. Therefore, we have the inequality b squared minus a squared m squared is greater than 0. We can take a squared m squared over to the other side. And then, because we know that a squared is a positive number, we can divide here without worrying about the sign reversing. We end up with b squared over a squared is greater than m squared. Now this can be solved to give us m is greater than minus b over a and less than positive b over a. If you're struggling to see why this is, you may like to consider a specific value for b squared over a squared. For example, let's choose 9. So if 9 is greater than m squared, what we are saying is that m squared has to be smaller than 9. And the values of m that would give us an answer smaller than 9 when we squared it are any values of m between -3 and 3. So this same situation has happened here with the b squared and the a squared. So because we know that m has to be between these two values, minus b over a and plus b over a, and we previously concluded that the limits, so the points where this inequality stopped being satisfied, those limits would represent the asymptotes of this hyperbola. That tells us that m must be b over a and negative b over a at those limits. So therefore, those are the values of m for the asymptotes. We're now going to find the asymptotes and vertices of this hyperbola. We're going to do that by rearranging it into the general form of the hyperbola equation and then reading off the values. So we're going to start by dividing the equation by 2. This is so that we end up with a 1 on the right hand side, which is required. We're then going to write it as a fraction. So in this situation, what we've done is we have written multiplying by 2 as being the same thing as dividing by a half. So this would be x squared over a half. We can also say that multiplying by 9 over 2 is the same thing as dividing by 2 over 9. So this would become y squared over 2 over 9. We can then factorise out and square each of these terms here. So we end up with x over the square root of a half squared minus y over the square root of 2/9 squared equals 1. These are now our values for a and b from the general form. So therefore, the vertices we know are at a0 and minus a0. So in this case, it will be 1 over root 2, 0 and minus 1 over root 2, 0. We also know that the asymptotes are at y equals plus and minus b over a x. We can simplify down this b over a. If we simplify, we end up with plus and minus 2/3 x. Now pause the slide and work out the asymptotes and vertices of each of these hyperbolas. So the first one has vertices at 1/2 0 and minus 1/2 0, and the asymptotes are y equals plus and minus 2x. The second one has vertices at 1 0 and minus 1 0, and the hyperbola has asymptotes at y equals plus or minus 1/3 x. Remember that the vertices can also be found by finding where the hyperbola intersects the x-axis. So in that case, you could do this by substituting y equals 0. Here's a summary of how each of the conics are formed from a cone. Now complete exercise 3A on page 63.